Good afternoon. My name is Carol Mikulak. I'm one of the project coordinators at the A. Proctor Group. Welcome to our webinar today on the protection of buildings on brownfield sites. In today's presentation, we plan to look at the sort of contaminates that you need to consider protecting against and what sort of impact they can have on the building occupants. We'll also consider the relevant legislation and guidance available to designers, then take a look at the practical issues around installation of gas protection systems and some of the common problems that can arise. We'll finish up by taking a look at the systems available and the types of project these are best suited to. The first contaminant we are going to look at is methane. Methane is a naturally occurring gas, which mainly originates from decomposition of organic materials. This gas production is most commonly associated with landfill sites, but peat bogs can also cause elevated levels of methane. Naturally occurring methane is colourless and odourless. Over the long term, any exposure to methane at concentrations over 1% can cause impacts on well-being such as headaches or dizziness, and can cause difficulty with breathing at higher concentrations. The problem most typically associated with methane contamination, however, is the risk of explosion. At certain concentrations in air, methane becomes explosive and will readily ignite. The upper and lower extents of this concentration are referred to as the upper and lower explosive limits. For methane in air, these are 15% and 5% respectively. Below 5% concentration, there is insufficient methane present to fuel an explosion, and over 15% there is not enough oxygen present for ignition. Concentration out with these limits should not, however, be regarded as safe. The most widely known incident arising from methane ground gas is the Abbeystead disaster, which took place in 1984 at an underground water pumping station in Lancashire. This was the first real disaster caused by ground gas, which helped start the ball rolling in relation to guidance and legislation that we now have to follow. Methane, which had seeped into the building from coal deposits deep underground, ignited and destroyed the facility during a guided tour for local residents. Subsequent inquiries and appeals found the building designers liable for the accident by failing to exercise reasonable care in assessing the risk on site from gas ingress, highlighting the importance of desk studies and site investigations when dealing with potentially contaminated sites. Fortunately, there have been very few other cases of methane explosions in buildings in the UK since. Carbon dioxide is another naturally occurring ground gas, most commonly originating from disused mine working where pockets of gas may accumulate. Carbon dioxide is an asphyxiant, as it typically reduces the concentration of oxygen in the air below critical levels. From 1% concentration in air, carbon dioxide will begin to cause headaches and drowsiness. 5% will begin to induce sleep or loss of consciousness, and 10% will lead to oxygen starvation, suffocation, and death. Higher concentration can cause sudden loss of consciousness, meaning victims may be rendered unable to escape before they become aware there is a problem. A recent example of carbon dioxide problems occurred at Gorebridge in Midlothian. In this case, site investigations revealed the presence of former mine workings under the site, but detected relatively low gas levels, therefore no requirement for gas protection measures. However, when housing was built on the site, incorrect foundations were used, and this, combined with construction of a nearby railway line, disturbed the ground and released high volumes of gas from the mine workings. Combined with a period of exceptionally low atmospheric pressure, this carbon dioxide entered several properties on the site, causing various health problems for residents. The severity of the problems, combined with the difficulties in retrofitting adequate gas protection, has led to a number of these properties being demolished, causing both significant cost to the local authority as well as extensive disruption to residents. The fate of the remaining affected properties is currently uncertain. Of all the common ground gases, radon is considered the biggest killer, with Public Health England estimating around 1,200 radon-related deaths per year. Radon is a radioactive gas produced by the underlying geology of some sites and is associated with the development of various cancers. Everyone is exposed to radiation from a variety of sources at all times, and in the UK, the largest source is a natural radon ground gas. That being said, typically these low levels of exposure do not cause any problems. The trigger level for dangerous radon exposure is 200 becquerels, and this can be reached where ground-produced radon gas concentrates in enclosed spaces. For comparison, the background level of radon activity is around 8 becquerels. Radon levels will change across the country as it depends on the geology of the area. For example, where granite is prevalent as the underlying rock. Radon maps are produced to indicate where the underlying geology is likely to produce significant amounts of radon and require protection to be provided to any development. In the white areas on this map, it would suggest that no protective measures are required, down to the darker areas where barriers and/or ventilation would be necessary. A word of warning with these maps though. They are based on the underground geology and historical readings, but may not accurately reflect the precise situation on site or how the development itself may have altered the pathways for gas flow. Current radon protection measures allow the use of a basic 1200 gauge polyethylene membrane, such as would be for damp proofing measure. Whilst this may be able to resist the permeation of radon, the ability of the membrane to withstand the build process must be considered. The approach to dealing with these types of contaminated land is based on pollution linkages. The primary linkages present in every situation are the pollution source, the pathway, and the receptor. This source, pathway, receptor model forms the foundation of risk-based design strategies for ground gas and VOC contamination. Source treatment involves taking action to break the linkage at the source, the actual pollutant itself. In very simple terms, this involves achieving one of the following outcomes. Destruction or neutralisation, whereby the pollutant is rendered harmless through the use of some form of treatment, such as adding a degrading chemical agent or a process such as heat. Removal, which can entail either removal of the polluted soil and disposing of it off-site or extracting the pollutant from the soil. Immobilisation, or trapping the pollutant by adding chemicals to solidify contaminants, making it impossible for liquids or vapours to escape. Pathway. A pathway management solution breaks the link between the contamination at the source and the building occupants by two primary means. Barrier systems, which physically block the passage of harmful liquids or vapours either at the source or the receptor. Dilution or dispersal, where ventilation systems are used to reduce vapour concentrations below harmful levels. Ensuring barrier and ventilation systems work effectively over the lifetime of the building is critical. Both specification and installation of these systems is more complex than it may appear, with an array of physical properties, tests and installation details to consider. It's also not advisable to rely on the membrane to provide 100% barrier to contaminants, so these systems are often used as part of a wider-ranging remediation strategy, particularly on heavily contaminated sites. Receptor. Receptor management is the most problematic of the three strategies, mainly as it can come into direct conflict with the purpose of the building or structure by placing restrictions on the occupants which may prove unacceptable. For this reason, receptor management is most commonly used as a temporary measure, while a longer-term strategy is developed. For example, restricting access to buildings during decommissioning of an industrial site, or evacuating residential properties in response to a nearby chemical spillage. Another more common example of receptor management would be health and safety requirements placed on contractors during remediation works, such as PPE or safe working practices. Gas protection legislation. There is a great deal of legislation and guidance available in this area to cover all aspects of the source pathway receptor model. In today's presentation, we'll be focusing mainly on barrier systems, so the pathway management part of the model and the legislation dealing with that. CIRIA 665. CIRIA 665 forms the underlying basis of gas design by classifying contaminated sites into what are known as characteristic situations. These classifications, from the least contaminated CS1 up to the heavily contaminated CS6, are based on detailed site investigations typically undertaken by specialist consultants. Once the characteristic situation has been defined, further guidance can be referred to determine the most appropriate gas protection measures to specify. BS 8485. BS 8485 is a code of practice for designing new buildings and conducting risk assessment on proposals. It was originally issued in 2007 and was a 28-page document. However, after a revision in 2018, it has now grown to about 100 pages. BS 8485 bases its guidance on site classifications from CS1 to CS6. A CS1 site has no gas present, while CS6 sites are heavily contaminated, almost to the point of being unsuitable for development. The site classification is then cross-referenced against the building's risk category. Type A buildings are domestic structures with small rooms and limited air movement, thus having a higher likelihood of gas building up to a dangerous level and increased exposure for occupants. At the other end of the scale, Type D buildings, such as warehouses, have large volumes and poorly sealed or frequently open doors, leading to lower concentrations of gas in the internal space. Buildings of these types are generally less continuously occupied. This assessment produces a point score for the building and site combination, and this sets the level of gas protection measured that must be applied. The first area in which points are allocated is the base construction of the floor and substructure. A poorly sealed element, such as beam and block floors, will score no points, while 2.5 points are given for a fully tanked waterproof basement. The main issues here are in the middle case, slabs with minimal penetrations. The degree of acceptable penetration is poorly defined by the standard, leaving it largely up to the designer what point score is acceptable. Further points are awarded based on the underslab ventilation provided, which can be either passive or active. The most basic form of ventilation is a pressure relief pathway, but little guidance is available on the degree of performance and robustness required. Beyond this are passive dispersal layers, which are classed as either good or very good based on how well the gas is dispersed within the layer. The passive systems rely on gas pressure, atmospheric pressure, and wind pressure to drive the gas flow out of the underfloor spaces. If properly designed and maintained, the passive nature of these systems makes them less prone to failure than active systems. Active systems use powered fans to remove gas, which in theory makes the systems more consistent and potentially more effective at removing gas. But problems can occur if fans are switched off for any reason, such as during change of tenancy or sale. For this reason, the points associated with active systems were reduced by the 2018 amendments, so that in most cases additional passive protection would be required. Finally, points can be scored by a properly specified and installed gas barrier membrane. Again, the guidance has been made tougher with these new revisions, and in order to score points, the barrier membrane must fulfil all the listed criteria. This ensures all membranes used on site are of sufficient quality and are properly installed. Under the old guidance, barrier membranes could score points under BS 8485 without providing any actual protection in practice. This could arise as much from damaged membranes or from poor workmanship sealing joints as from low quality material. NHBC Traffic Lights. The NHBC use a traffic light system to remove ambiguity from the classification and streamline the process. This is not intended to remove the need for specialist assessment, but rather to simplify the implementation of measures based on their findings. A green site is roughly analogous to CS1 and no special protection measures are required. Amber 1 sites align with CS2 and can be dealt with by using a simple membrane and passive subfloor ventilation system, as the risk is comparatively low. Amber 2 CS3 sites, being higher risk, require a specialist contractor installed membrane with additional verification of the membrane integrity. Red sites are generally considered unsuitable for private housing developments, and if built on at all, will require a more in-depth and specialised approach. A requirement of BS 8485 is that the membrane installation be verified in accordance with CIRIA 735, another important document for designers dealing with gas protection. Released in 2014, CIRIA 735 details requirements for validation and inspection, and means that more or less every gas protection installation will require fully independent inspection and verification of at least some percentage of the development. This CIRIA document also details the types of testing that can be undertaken, from simple visual inspections through to air, lance and tracer gas testing. Not all of these testing methods are suitable for every site, and these limitations are discussed in the CIRIA documentation, making it well worth reading for anyone involved in these types of projects. The purpose of mandating this testing is to ensure the system, as installed, will perform as designed and ensuring that performance is maintained throughout the design life of the installation. The requirement for inspection can be reduced if NVQ Level 2 installers undertake the job. So in this way, CIRIA 735 aims to upskill the groundworks installation industry by reducing the associated costs of verification and inspection to offset the expense of installer training. A further consideration, dealt with primarily via CIRIA documents, is VOC contamination. VOCs, or volatile organic compounds, are defined in CIRIA 716 as organic compounds that are volatile under normal environmental or atmospheric condition. They may be found in the ground in the solid, liquid or dissolved phase form, as well as in gaseous phase. VOCs can be both man-made or natural and have a wide range of applications and sources, being found in everything from paints and coatings to plastics and cleaning products. Hydrocarbon fuels, such as petrol and diesel, are also forms of VOC. When specifying geomembranes for VOC applications, it is important to remember that chemical resistance and vapour permeability are not the same thing, and membranes that are highly resistant to liquid VOCs may not be suitable in a VOC vapour barrier application. Conversely, membranes which resist VOC vapours effectively may lack the resistance to be used in the presence of liquid hydrocarbons. That's not to say the chemical resistance is not important, as the barrier must be able to resist exposure to adverse conditions in the longer term without negative effects to its performance or mechanical properties. It can't always be guaranteed that the VOCs will remain a vapour, as the water table may rise and bring the membrane into contact with the VOCs in liquid form. The actual VOC resistance is only one facet of membrane performance that must be considered. The CIRIA 748 document gives important guidance on the specification of membranes used on VOC contaminated sites. Membranes must also be able to resist degradation processes such as oxidation, particularly if they are based around foils. Once again, there is a series of linkages that must be considered as the basis of good, robust design. Foil membranes are often considered to be a perfect solution, as they offer high resistance to all types of vapour, but it must also be taken into consideration that the foil responsible for this resistance can degrade or break down over time. It is not uncommon for a membrane to pass the vapour permeation tests, then subsequently fail due to degradation associated with oxidation, where vapour has permeated through the cut edges of the membrane. As part of an appropriate overall design, a membrane of lower resistance to a liquid contaminate may still be suitable provided exposure to that liquid form is minimised, for example by means of source remediation or by ensuring the barrier is located in the structure, such as that contact is impossible. We'll now move on to take a look at some of the common installation situations and the difficulties that can arise with each. We'll begin with corner details, which are probably the most common detail present on every site. This corner has been cut and resealed using flashing, but has been left unsealed at the corner. The membrane has also not been pushed into place properly, so any subsequent concrete or screed pours will overstress the membrane, which may lead to tearing and subsequent gas ingress. In this case, the membrane has not been extended to close the cavity wall, leaving open a pathway for the gas. The membrane is also roughly folded into place, which may cause problems when it comes to installing further courses of brick or blockwork. The most reliable and time-efficient method of getting good corner joint is to use pre-formed corner units. In most cases, however, these corners will need to be adapted to fit precisely into place. The important part of the corner, the integrity of the actual corner point itself, can be maintained by carefully cutting the corner unit across the middle and sealing both the top and bottom sections into place, as shown here. This ensures the corner area remains fully gas tight. Another detail found everywhere is the simple membrane joint, where joints between adjacent runs of membrane commonly cause problems. The most obvious problem is missing sections of sealing tape, creating a path for gas to bypass the barrier, but tape joints can cause other problems. Here we can see where the tape run has not adhered to the membrane, where the membrane is not sitting flat on the substrate. The most effective method, and that used by the majority of NVQ qualified installers, is to weld membrane joints. This not only saves on the cost of tape, but it is far more tolerant of weather and site conditions, as tape adhesion is not an issue. Successful tape jointing requires a clean and dry membrane surface to join, and temperatures within the tape's operating range, typically 5 to 30 degrees. Assuming that these conditions are met, however, the optimal procedure for a successful tape joint is shown here. We developed this detail in response to the guidance regarding site inspections. By moving the butyl tape joints to the edge of the lap, it becomes far easier to ensure the joint has been done correctly. This positioning of the tape also ensures any concrete or screed poured on top of the membrane cannot enter the joint and put additional pressure on the integrity of the joint. Detailing around stanchions is a little more difficult, but does not pose too many problems if the method shown here is used. The most important thing to note here is that the flashing tape used is of good quality and matched to the membrane used. As manufacturers, we recommend and supply tapes that we know to work well with our membrane systems, and this advice should be followed. The flashing tape should be rolled into place without leaving gaps underneath. Flashing tapes are usually less resistant to elongation than membranes, so it's important these areas are fully adhered to a properly supported substrate to limit the potential for movement. The rounded corners shown here are also important, as these are less likely to lift than sharp corners and put less stress on the membrane and tape interface. Although it may seem obvious, it is also important to ensure the gas-tight layer is continuous. If, as shown here, the stanchion is in the centre of the concrete column or pile cap, the entire area must be sealed. Pipe penetrations are another area that is important to get right, as they are a common feature on many sites. These images show some of the more common problems that can occur. In the first case, the supplied top hats did not fit properly, so the installers decided to get a little creative. While it's possible this detail may work to provide a gas-tight seal, it's by no means a given and would be almost impossible to verify. In this second case, the smaller pipe appears to have been relatively well sealed, but the larger is not sealed at all, and corresponds to a lap in the membrane, creating additional complications. The close proximity of the pipes to each other also makes detailing and sealing using proprietary top hats difficult. Here we can see the correct procedure to provide a gas-tight seal to a pipe penetration. As with columns, this is not particularly difficult to achieve. Again, as with stanchions, ensuring the membrane is cut as little as possible and the top hat is smoothly seated onto the membrane is critical. The flashing tapes should be firmly adhered in place and properly supported. The general conditions around a site are often as important as specific details when it comes to validation of membrane installations. In these images, you can see that patches have been applied to the membrane haphazardly and messily. The marker spray is still visible around patches, indicating that the applied patches are too small to give the required overlap. In this case, we can see the rebar laid directly onto the membrane with no protection fleece or board used. The fleece is not only important to prevent direct puncturing of the membrane, but also to prevent damage from cutting using saws and grinders. These processes produce large amounts of sparks which, if they contact the membrane, can melt holes and cause significant damage. So while a small increase in cost per square metre to specify a fleece or protection board may seem unnecessary, the effect it can have in reducing remediation costs and delays is more than worth it in most cases. Membrane systems. The choice of material used on site must be informed by the permeability, chemical resistance if applicable, physical properties, and expected installation procedure. All the possible membrane types in gas protection have pros and cons, and it's important the properties of the material selected adequately address the risk factors present on a given site. When it comes to building on contaminated land, there are no magic bullets or one-size-fits-all solution. So now let's look at some of the most commonly used geomembrane types. Polypropylene, or PP. PP membranes have good elongation characteristics and are highly flexible. This makes them a good choice where settlement is likely or where complex detailing must be undertaken. PP is, however, relatively permeable to most gases and is expensive. PP membranes also have poor adhesion characteristics and therefore require specialist welded joints rather than tape jointing. PP membranes are traditionally used in water containment applications, due mainly to its suitability for use on larger unreinforced areas. High density polyethylene, HDPE. HDPE is cheaper and offers good resistance to puncturing, but in comparison to PP is rigid and therefore both difficult to install on complex details and prone to stress cracking. Any bending of the membrane to angles over 60 degrees is typically not recommended due to its detrimental effect on performance. Because of this mechanical weakness, HDPE is better suited to large uninterrupted floor areas, which is a good fit with the roll sizes they are typically supplied in. Like PP, HDPE membranes should not be tape jointed and require specialist welding contractors and verification. Low density polyethylene, LDPE. LDPE membranes are standard DPM materials, which are cheap, easy to handle and readily available, but can be low quality and generally not suited for gas-resistant applications due to their high permeability and limited resistance to damage and UV. LDPE membranes' resistance to VOC vapour transfer is particularly poor, and these membranes can degrade rapidly if directly exposed to chemical contamination. Low-grade LDPE can also have problems with manufacturing tolerances, resulting in a material that, while water resistant if undamaged, will not deliver consistent and robust performance in gas protection applications. Reinforced virgin LDPE. Reinforced membranes made from higher quality virgin LDPE are inherently more consistent, as good control of thickness and material tolerance is critical for achieving a good lamination with reinforcement. This reinforcement also greatly improves the membrane resistance to tearing and damage while allowing the membrane to retain its flexibility. This results in a good balance of durability, performance, ease of installation and cost. It is, however, important when using these membranes to have a good understanding of the risks present on site to ensure the vapour or gas permeability of the membrane is adequate for the application. Foil membranes. Adding a foil core to LDPE or HDPE membranes dramatically increases the gas and vapour resistance of the membrane without a correspondingly dramatic cost increase. This makes them a good option where elevated risks are present and it's not feasible or desirable to use additional techniques, such as source remediation, to lower the concentrations present. There is a common misconception that because the membrane has an aluminium foil in its build-up, that this will offer good all-round protection from contaminants. While that may be true, elongation and foil degradation can be an issue. While the base plastic membranes are able to elongate to some extent, this is not true of the foil layer within them. If settlement occurs, the corresponding stretching of the membrane can rupture the foils, leading to a significant deterioration in gas barrier performance. It's therefore critical, when using foil-based membranes, to make sure settlement is minimised and expansion joints are properly detailed to avoid overstressing the membrane. Foil membranes, such as the A. Proctor Group's Protec GM Super, are generally considered a better fit for common ground gas applications such as methane and landfill gases. When dealing with VOC contamination, a dedicated membrane such as Protec VOC Flex will offer a more comprehensive solution. Specialist film laminate membranes. These types of membranes are similar to foil core membranes, but replace the foil with a specialised film such as EVOH. This allows the performance of the membrane to be adapted to meet application-specific barrier requirements, so these membranes are typically more common where VOC or chemical contaminants are present. EVOH membranes offer good resistance to a variety of VOC contaminants, while still allowing the membrane to retain good physical performance characteristics such as flexibility and elongation. Liquid applied membranes. Liquid applied membranes are ideal for complicated foundation detailing and uneven surfaces. The downside to these systems is that it's not always easy to determine the tolerance of application, such as continuity or thickness of coating. Liquid applied systems do, however, make a good companion to sheet membranes where complex details must be sealed. So we've seen throughout today's presentation that the most important factor in dealing with contaminated sites is good design based on good information. Whether it's conducting a thorough investigation into the historical uses of the site, or ensuring the correct membrane for the job is well installed by contractors, a good understanding of the risk factors involved and a well-developed holistic remediation strategy is key to achieving a safe and good value solution. Technical support services. With over 20 years' experience in ground gas protection, the A. Proctor Group have always taken this approach, supplying both a range of fully tested membranes and comprehensive technical support and design consultation throughout the specification and installation process. Perhaps the most important aspect of this is providing hands-on assistance with detailing of membranes and the production of drawings to allow correct installations to take place. We also provide a full library of BIM data and template constructions for all our products, available in both Revit and IFC formats for compatibility with a wide range of software and systems. Finally, our on-site toolbox talks ensure the entire project team is confident working with our materials and has a full understanding on how they work and the benefits they bring to the projects. That concludes our webinar today. Many thanks for your time.
Good afternoon, everyone. My name is Keira Proctor and I'm the Managing Director here at the Proctor Group. I'd like to thank everyone for joining and listening to our webinar. I hope you find it enjoyable and informative. Just a quick one, the CPD certification is available on the link underneath the video, should you wish to have it. We've had some questions sent in via email and also quite a number on the YouTube chat. So I'd like to introduce Chris Hayes, who is our Ground Protection National Sales and Technical Manager. He is here to answer your questions.
Hello there, good afternoon everybody.
Good, okay, so please feel free to add any questions as we go, should any come into your mind. So we'll just ask away, Chris, if you're ready.
Okay, that's fine, yeah.
Okay, so the first one from Tom Fisher. How do you use two different types of tapes when sealing a gas membrane?
Okay, well, initially we use a double-sided butyl tape, which would initially seal the two sheets of membrane together. We usually recommend a minimum of 150 mil overlap, and then to prevent sort of concrete getting in between the joint or people tripping over the overlap membrane, we then use a single-sided tape to seal the overlap to complete, making the overlap actually having a double-sided tape in between and an overlap tape on top, so a dual system tape.
Okay. When it comes to sealing pipe penetrations, they're always so close to the wall. My experience with top pats is that they are rigid and therefore don't seal very well in this instance.
Okay, that's a very good point. Our standard top hats are quite rigid, which does prevent them from being bent, very easily. They're not very flexible. But what we do have is a range of flexible top hats as well, so that you're able to actually bend them and tape them to the side of the wall, so that if your pipe penetration is that close to the wall, you're still able to use the top hat because the base plate of it is flexible enough to bend.
Okay, good. Can Proctor visit site to check and sign off the gas membrane that's been installed by a ground worker, and would that comply with CIRIA 735?
Well, whilst we're happy as a company to assist anybody installing our membranes, we're quite happy to go to site and provide toolbox talks, go through some of the installation details with them. Unfortunately, that's as far as our involvement can go, because as you mentioned there, CIRIA 735, which is all to do with validation of the membrane, which is part of what you have to do to get your point score for a membrane under the British standard. It means that the membrane has to be independently validated. So that means, as it says in the name, an independent validation company has to go to validate the membrane and sign it off from their point of view. So in answer to that, no, we can't.
Can't do that. And is that something we could help with? So would we have kind of a list of recommended verification companies that we could send on to people if they asked?
Yeah, that's correct. We have a list of contacts that we use within the industry that can assist in that matter. I think the other thing to point out here as well is that it generally is better to have the membrane installed by a specialist, which will also aid in having the validation passed at the first attempt, rather than sort of delaying site because the membrane's not been installed properly. So that's another key thing, and we also work with a lot of industry specialist installers as well that we can provide you contact details for.
Okay, a couple of good questions from design coordination here. For a bank of pipes or services in pipe with 110 mil, with 50 mil outside of the pipe, how is it suggested to seal individual collective, and what is the suggested minimum between penetrations?
So I assume here we're talking about where you would have a line of perhaps different size pipes all in sort of close proximity to each other. It is very difficult to seal that type of situation, and we're trying to avoid having the pipes that close together wherever possible. But we can do it, and have done it in the past by using multiple top hats that are all as one. So essentially we could have a top hat that would give you 6 different diameters of pipe within the one top hat, but there does have to be at least a 50 mil clearance really to be able to get those top hats to work.
Okay, and just while we're on a question about the pipes, another question that they've asked is there a liquid mass filler, similar pore properties to concrete, a bit like Hilti fire compound, that can be poured into and around pipes and upturned membrane?
We have a liquid gas membrane that we could potentially paint around the services. I'm not actually familiar with that Hilti product in particular. I mean, this is something I could probably look into further after the webinar if that person would like to sort of speak to me individually, and I can find a little bit more out about that for them.
Absolutely. Okay, good. Do you have, do Proctor, I presume they're asking, have a combined ground gas and waterproof membrane for use in below ground structures?
The issue when you've got gas protection and waterproofing coming head on together, it means that we have 2 different types of standards that we have to look at. For example, for the gas protection, we would look at the BS 8485 2015 document, but also for waterproofing you have to consider the BS 8102 2009. Both have different sets of sort of criteria, and obviously waterproofing is also based on risk assessment and can be quite complex in nature. Although we do have a gas resistant self-adhesive membrane, because normally with waterproofing, it may require more than just a membrane to completely seal it for waterproofing purposes. We don't have currently in the range all the other waterproofing products that would initially make that a watertight system. So really at the moment we would probably say that if it was required to do waterproofing and gas protection, we don't currently have something suitable at the moment.
Okay. Another one that came in via email about applications was, can you use a standard DPM for protection against radon?
Okay, there's always been a bit of a myth with the fact that standard DPMs can provide you radon protection. The problem is with standard DPMs is that they're made from a very high amount of recycled products. This also means that they're not very robust, so that they're highly likely would fail the construction phase after the membrane's installed. And obviously if the membrane gets damaged, then essentially it lets radon through. Really, if you're going to be using a radon membrane, you should be using virgin polymers, virgin material, and something that is specifically independently tested and is proven to protect against radon. So my advice would be, never really use a standard DPM, always use a specific radon resistant membrane.
Okay, good. Based on the NHBC Traffic Light system, is it correct to say that verification is only required for CS3 and above?
With NHBC, yes, their situation is that the membrane, if you're on an amber 1 scenario, the membrane can be installed by the ground worker if so wish, providing that you get a subfloor void that gives you a complete volume air change per 24 hours, then they would accept that as being an amber 1 scenario. If it was an amber 2 scenario, then yes, essentially they look for the membrane to be installed by an MVQ level qualified installer, and they would want to see that independently verified in accordance with CIRIA 735. I would always advise to check with the NHBC on those things, because it depends on whether they are comparing it also to the British standard. Because again, if you look at the British standard in any applications where you use a membrane, if you want to get the points for that membrane, it does have to be verified under CIRIA 735. So there might be a little bit of conflict in the two guidance documents. So it's always worth checking with the NHBC engineers on that particular project.
Okay, we had another one via email just before I go on to a question from Michael Jones about a timber frame application. So one we had through email was, what type of substrate should the gas membrane be laid on?
Well, really, we ask for either a concrete blinding or a sand blinding, at least a minimum of 50 mil thick. What we don't really want is people laying the membrane directly onto hardcore, where there's potential sharps that could puncture the membrane from below. Similar to when we lay the membranes above suspended floors such as beam and blocks, you tend to get a lot of mortar snot and concrete dripping on the actual beam and block floor itself. And again, if you were to put a membrane directly over that, it can be easily ruptured when people are walking over the top of it with the boots. So again, in that scenario, we'd either suggest that they actually clean the surface of the beam and block floor and make it good, or alternatively they could use a protection fleece, which is something we have within our range that you could put down to help make the substrate better for the membrane that's going on top. Okay,
and coming on to the question, when using timber frame, how do you seal the DPC where the sole plate penetrates it?
If we're going to look at that type of detail, then essentially there are two ways of looking at it. The first is that we could position the membrane or DPC in the block work that would be below the sole plate. So essentially you're taking it into the joint of that particular block that's below the sole plate. So you're not actually penetrating the DPC or the membrane at all, because it'd just be fixed into the top of that block. Alternatively, if we do have to position the membrane and close the cavity going through the sole plate, then we would recommend using some of our TF tape, which is 100mm butyl double-sided tape, which would be positioned above the gas membrane or DPC. And then the idea is that the sole plate would then be fixed through the tape and into the block, and the butyl tape that we use would then self-seal the fixings when they penetrate it to give you that gas seal.
Thanks, Chris. We just have 3 more questions that we've had via email, so if any other people that are still listening or watching, please feel free to type them in on the YouTube chat there. So Chris, can you use a standard foil gas membrane, i.e. Proctor GM Super, for hydrocarbon VOC protection if used above a beam and block suspended floor?
Okay, this is always a bit of a tricky sort of question to answer, and it's not a straightforward one really. Generally speaking, we would tend to use a specific hydrocarbon VOC membrane above a beam and block floor in the form of something like our VOC Flex. The reason for that is because a membrane such as our VOC Flex is classed as what we call a specialist film laminate, which was obviously covered within the webinar, but a specialist film laminate such as our VOC Flex doesn't contain the foil within it. So essentially, if we were to use GM Super, which is a foil laminate membrane, where you potentially cut the membrane to create the overlaps, it would then potentially expose the foil within it, and then the foil can, due to oxidization process, can cause the foil to delaminate. So this is generally what you would get if it comes into contact with some hydrocarbons and VOCs. There are some instances, depending on who's installing it, whether it's a specialist installer, whether the membrane is cut in any position or not, and depending on what concentration and what particular type of hydrocarbon it is, you can get away sometimes by using GM Super. But really, I would suggest that you speak to us when you've got any of those projects, so we can take a look over the details and make sure what we're doing is right.
Hold on, I've done that one, sorry. Should protection board be used above the membrane?
It's always good practice to make sure the membrane's protected. That can be done in the form of either a specific protection board or the insulation that's perhaps going above the membrane and below the screed, or even in the form of a geotextile fleece. So it's always wise to protect it, because obviously what we don't want is damage after we've put the membrane down, because again, that would obviously then allow the gases through. So yes, it's good to put some form of protection down.
Okay, and our last question that we have here. During the webinar, it mentioned the use of preformed units to seal corner junctions. Do Proctor Group manufacture preformed units for other complex junctions?
Yes, we can do. It's again always wise, if you're undertaking an installation of a gas membrane yourself, i.e. you're not using a specialist installer, to use complex junctions, to use preform units, where there are complex junctions, because it obviously helps negate poor workmanship and detailing, which could be a pathway for the gases to actually get into the building. If you've got any particular projects where you have complex junctions such as steels, or ground where you've got the walls coming in at sort of different angles and all sorts of stuff like that, then please contact us and we can have a look through the drawings, and we can then put a package of specific bespoke units together for that particular project.
Okay. Thanks, Chris. That's great. That's all the questions that we've had on YouTube and via email. If anyone has any additional questions, you can send them to technical@proctorgroup.com. They'll be picked up pretty much immediately and filtered to Chris, who will then contact you directly with any questions that you may have, project related, product related, anything you like. In terms of what happens next, everyone that's registered or has listened to the webinar, you'll receive a link to the replay. So we encourage people, if you want, please send it to colleagues around your offices, anyone that you may think may find it interesting or informative. There's also a link to a feedback form. If you have time, please fill this out. It allows us to kind of, gauge how well we've done, what we could do better, and shape future webinars. So if you have time, we would really appreciate the feedback. Thank you very much again for attending. We hope you really enjoyed it, and thank you very much to Chris. And I hope everyone has an